Good morning, students. We'll continue with our lecture, that is, we'll continue with the topic virtualizing the unvirtualizable. So, yesterday we had completed till the techniques for efficient virtualization. So, today we'll be starting with virtualizing the unvirtualizable. So, what is virtualizing the unvirtualizable? Means which is not looking real, but somewhere we are trying to make it virtual so that it can be accessed by all. So, the question can occur, suppose when I say virtualizing the unvirtualizable, the question in your examination could be like this: how virtualization is achieved with binary translation in Intel before development of virtualization technology, explain in brief. So rather you can go for a twisted question with this also, that is, how can you do the binary translation of unvirtualizing the virtualization technology in the current situation. So before the development of virtualization technology, binary translation and hardware features that were exist on x86 hardware, such as the processor protection rings, was the solution to achieve it. So processors were changed, they were increased in the capability in the prior 1980s and 1990s. But after 1995, when the virtualization actually started, for longer period of time x86 hardware was used and ring system was used, that is, ring 3 is least privileged, ring 2 is there, then ring 1 is there, and so on it was there. So binary translation was done. The binary translates, rewrites the guest operating system running in ring 1 while the hypervisor runs in ring 0. So as you can see, a hypervisor is running in ring 0. Ring 1 is for your actual process which is running on the guest operating system. Ring 3 has n number of virtual machines. So altogether ring 1, 2 and 3 ring levels were set. So ring 3 is the least privileged and not allowed to execute privileged instruction in this ring. They cannot execute their own instructions, they have to sit. Normal user process execute in ring 3. Normal user, not the admin user, is in the ring 3. Then the most privileged ring is ring 0. The most privileged, that is the most preferred ring is ring 0. Then and it permits the execution of any instruction. So in the hypervisor, wherever the ring 0 is, ring 0 will have the most privileged, and the execution instruction is also done from ring 0 only. It has that rights and permission. In normal operation, kernel runs in ring 0. In normal, whenever you go for a normal operating system, your kernel will be in ring 0. Ring 1 and 2 not used by current operating system. So 1 and 2 will not be used by the current operating system. They will be only for the user operating system, who are normal users are there, for that only. Hypervisors were free to use them as they are satisfied. So hypervisors will make a climate for that hardware and the OS in the guest operating system for making a communication two-way. You can see this arrow. Then ring 0 is in kernel mode. Ring 0 will be in kernel mode, other all are in the virtual machine. Then as well as ring 3 as user modes. So hypervisor will keep the solutions in the ring 3 as user mode. The guest operating system runs in a layer of intermediate privilege, in which is ring 1. So guest operating system will run in the ring 1 as shown in the figure. Then the kernel is privileged with compared to the user processes, and access violation will occur if user program try to access any kernel memory. So normal user process cannot directly go and talk to the kernel process. It has some levels, and every level it has go through to access the value. So there are certain basic blocks also which are being there in the hypervisor to write the code. If there are sensitive instructions, the calls can be jump, call, jump, call, trap, return are the basic, you can say, blocks which are being used for writing the instructions. And then the instructions are, if the instructions are not sensitive, it can execute natively, it can simultaneously get executed, especially given that the hypervisor configures the hardware cautiously. So it's the total process of the hypervisor, that the hypervisor will look into it and then properly execute the instruction. Once the execution of basic block is over, if the execution of whole process is over, then control it is returned to the hypervisor. Then again the control is returned to the hypervisor, again all the controls have come to the hypervisor, and which then finds its successor, that the next process will pop into the process. Alternatively, carrying out binary translation on all the guest operating system code running in ring 1 is common practice. So alternatively, every time accessing one process at a time from the guest operating system from ring 1 is a common process ring which is being followed every time. Then if we take this same situation here, see, you can see it's type 1 hypervisor. If we take this same situation for hypervisor 2, type 2 hypervisor, also use the same technique. If we go for this whole process, it will be same for hypervisor type 2. Type 2 hypervisor must control the hardware at lowest level. So lowest level manipulation of hardware cannot be carried out from user space. So normal user space does not has any right. The total hypervisor will look into that process. Then the next is, are hypervisors microkernels done right? So this is the question, or is that there any solution? That if you can see that they have connected one hardware, they have connected one hypervisor with a microkernel, and they have their own methodologies which are running onto it. Means, suppose if I say that I have an hardware on which I have type 1 hypervisor as well as microkernel, but on my type 1 hypervisor I am using the same hardware but with the method called true virtualization. Whereas when I say I am using a microkernel on the same hardware and I am using a modified Linux on para virtualization. So these are two different scenarios, two different methods, and accessing same resource. So see, two different scenarios, that is unmodified Windows, modified Linux, true virtualization, para virtualization, two different methods. So how can you say that this is our hypervisors microkernels done right? Means both can be accessed at the same time or not on the single hardware. So the solution is, instead of carrying out sensitive instructions, the para-virtualized guest executes hypercalls. So para-virtualized guest operating system will check for the sensitive calls, that is the hypervisor, just like a user program. So this will do a task of parallelly accessing the hypervisor sensitive instructions, as well as guest OS makes call to hypervisor just like a user program. Now guest OS is also called like a normal user program. Hypervisor defines an interface including collection of procedures that guest OS can use. So hypervisor, what it will do, it will create an interface in such a way that it will use these processes as the normal collection of procedures which will be useful for the guest OS. And this set of procedures form API, that is application programming interface. So this set of collection of interfaces like the different guest OS will create an API, that is application programming interface. If all the sensitive instructions from the operating system are removed and only hypercalls are carried out to get system services like IO, then hypervisor could just be like a microkernel. If there would be no sensitive instructions in the hypervisor, then it would work like your normal microkernel only. But here as there are sensitive instructions, it would act as same as like your normal guest operating system for your hypervisor, as well as source code of guest OS is not available. Your guest OS is a time being operating system, so the source code is actually not available with the system, and the hypervisors emulated the complete machine. So hypervisor, what it will do, it will go through the whole machine to check the process. In future, there can be a scope to standardize the hypervisor microkernel API and to design the following operating system to invoke it in the place of using sensitive instructions. So rather than taking these sensitive instructions on the separate machine or the separate hypervisor, if there is a scope in the future, it can be like the same, and we can create another process to just handle the sensitive information or sensitive instruction. This could turn the virtual machine technology easier to support and use. So this can be a more easier and convenient way if we directly separate the hypervisor and the microkernel, or we can merge together, but it could not handle the the sensitive instructions. Now virtual technology hardware supports two machines. So here there are two machines, different machines they have shown, that is unmodified Windows and modified Linux. So two guest operating system, one is unmodified Windows, another is Linux, is present for execution of sensitive instructions. So both have their own instruction set of instructions, and which then emulates it in the instruction. The hardware issues to a trap to the hypervisor, which then emulates it to it and returns. So what happens is, due to their own trappings, that is their own instruction trapping, they will talk to their own microkernel or an hypervisor and return back. As Linux is modified version, it does not include any sensitive instructions. So as Linux is a modified version, it's a updated version, so it will not have any sensitive instruction. For carrying out any work, modified Linux makes a hypervisor call in similar manner an application program makes. So it will be as similar as your normal application, how it works on the system. Hypervisor is a single program containing two parts. So hypervisor generally is a single program which is running on your hardware, but it has two parts, that is type 1 hypervisor and the other is microkernel. Emulation of sensitive instruction is carried out by type 1 hypervisor. So if there is a sensitive instruction, it will be tackled out by the type 1 hypervisor, and if the hypervisor need to run only para-virtualized guest operating system, emulation of sensitive instruction is not needed, and true microkernel offers very basic services. So if my hypervisor wants to run a para-virtualized method, for that it should not have sensitive instruction then. That is the reason this dotted line is been put, and that is the reason it has been come up with a solution, that is microkernel, to get those para-virtualized system to be done, that is to follow the process with a basic service and basic resolutions to resolve the issue of availability of different types of hypervisor in market. So there are a lot of hypervisors now in the market with variations, and it does different API, VMI, that is virtual machine interface, is used. Normal application programming interface, then you have virtual machine interface nowadays, so that you can work for such sensitive instruction. If not, rather than microkernel, you can go for an interface process. The kernel is customized to invoke special procedures. So kernel will be there to invoke special procedures, and these procedures are generic. So generic means it has come generation to generation, and that is called as VMI, that is virtual machine interface. Next is, are hypervisors microkernels done right? So priorly it was hypervisor microkernels done right. Now are hypervisors microkernels done right with different machines at a time? That is, if I separate each and every machine separately, what can be done? That is, see here, I have done sensitive instruction separately, I have done hypervisor call separately, I have done hypervisor call and different servers on different libraries. You can say VMware to VMware, Zen library to Zen library, but their guest operating system is Linux and they have their own servers as well. So bare hardware, VMware and Zen. That is, bare hardware means all the sensitive instructions can be followed. Then that is the reason it's hypervisor 1. Bare metal is hypervisor 1. Here you have guest operating system and their own servers. Here also you have guest operating system and servers. So Zen is different server, VMware is a different server. Hardware support for nested pages table. Hardware support means if you have nested pages, if you have indirect hardware support, what can be done? Due to large amount of overhead involved in handling shadow page tables, a hardware support for nested page table is added into the chip. So on your chip, this nested page table is been somewhere included, and for what it is for the overhead of data which is been overloaded onto the chip. AMD call is nested page table and Intel it is referred as EPT, extended page tables. Additional manipulation of page tables are carried out in the hardware without traps. So without any trapping, such nested page tables are being formed. We have guest virtual addresses, guest physical addresses. Yes, guest. So there can be a number of addresses, that is guest coming temporarily, guest operating system, they will have their virtual address. If guest is setting on changing its variation and coming to the physical address, and some another operating system is going on to the place of guest, then it will have its physical address also and a virtual address also. Then these nested page tables can be included also in the machine physical addresses. Without EPT, it was the job of the hypervisor to maintain the shadow page table. So with EPT, that is extended page table, it is the work or task of your hypervisor also. After the inclusion of EPT, the hypervisor still maintains additional set of page tables. So hypervisor will also maintain a set of page tables which have occurred. But now the CPU is capable of handling much of the intermediate level in the hardware also. Nowadays CPU also can tackle out with such some intermediary problems of these hardware. Next is cloud. So what is basically cloud? Cloud is your National Institute of Standards and Technology defines characteristics of cloud. But what is cloud? Anybody who can refer cloud as, like, cloud is something which is visible, which can be used for storage, but somewhere it is not actually in your system. So that is being referred as cloud. But does we say that in natural like environment, do we say that only one cloud is there? No. So virtualization technology is a key responsible for the rising of cloud computing. So for the technology of virtualization, we need something which is called as cloud, and that technology is called as cloud computing. So we need a virtualization data storage, and for that storage we require clouds. So clouds are public and private, so they have two authentications. Cloud can be public, cloud can be private, and each other different things to their user. So they will provide each different services on their part for the user. Some offer user access to physical hardware, but most virtualize their environments. Some offer bare machines without virtualization, but others offer software that is ready to use. So there are certain variations in giving the services or to the users, depending on if it is bare metal, if it is not bare hardware, it is virtualizable. If it is not virtualizable, then it is accessing the software only. So these are the technologies which my cloud is providing. So what are the characteristics of cloud? As per National Institute of Standard and Technology, following are the 5 important characteristics of cloud. So first one is on-demand self-service. So users should be offered resources without human interaction. So if I want to use my drive, I do not have to pay somewhere. I do not have to ask somebody to access it. I just log in it with my email ID and I can use my cloud service that is on demand. When I want it, I have that service that is on demand self service. Second one is broad network access. So it's heterogeneous, anybody can access it anytime, anywhere they go. It can be easily available, that is called as broad network access. Resource pooling. Resource pooling means sharing of resources is there because multiple users are using it. That is, multiple users should be able to pool computer. Pool means one device is being achieved by everybody. Everybody is using that one actual service, is called as pooling. POOLING, pooling. Computer resources owned by the provider. So whatever services my cloud service is providing, to access that service everybody can use it, and that is multi-user system. That is, resource pooling is being done. Rapid elasticity. Users' demand should be fulfilled by acquiring and releasing resources automatically. I do not have to go and ask for my services to be released by somebody. Acquiring, using that and storing the data can be done. So it's rapid elasticity. At that moment of time, the reply is being given. Measured service. The service offered by cloud provider and resources used by user should match and both should agree on the same. So the resources which are there, the terms and condition policies should also be followed while using the cloud service. With this, we'll stop here for this lecture. We'll continue the next topic in the next lecture. Thank you.